We're looking at the signal soother at a system level today. The last video I made you should definitely watch, but this piece of paper is from it. The only difference is I've added these blue highlighter marks here. We're going to take a giant step back and look at how this works in the system here. So these blue highlighter marks are each one of these. So every one of these is this circuit right here, and it's also all of those as well. If we look at this guy, we had these orange and these green guys. The orange ones are reproduced here. These were all of the HVDC negative and HVDC positive referenced circuits. And then the green ones were all of the middle cells, so the evens or whatever, and these were the odds. We are basically going to look at this again, and this is a technical video as the last one was. So we have our HVDC bus, HVDC positive and HVDC negative, and here is where the next cell lithium batteries go. And so you can see that all of the current is sourced through here, up through there, and then over, and then it actually comes out to our drive module. And in this module, this is a conceptual thing. This isn't the complete schematic, but this is the pertinent part of it here. When we turn the key on, we have a pre-charge resistor that charges our HVDC bus. And so this is our IMA motor or our electric motor bus. And so here's our motor PDU, the power delivery unit. These terms are, kind of borrowed from the Honda Insight, but it's the same general architecture here. When we turn the key on, we first have to charge the HVDC bus. We can't just hook a relay up because at 250 volts, this relay is going to explode when we try to charge essentially a 0 ohm capacitor. So we have to do it slowly through a pre-charge resistor. Say, I don't know, 15 ohms. I haven't actually looked, but 15 ohms would be maybe 17 amps peak inrush current, and then it would die down very, very quickly. Our HVDC bus charges. And so all of that current again sources through here. And you notice that current goes through this service disconnect here, which is the thing you pull out before you take the cover off of the battery, and it splits the pack in half. But really it splits it where B1 through B4 are on one side and B5 through B14 are on the other. Now this service disconnect is really, really important because you want to make sure that if your technician accidentally touches B14 and B0 or anywhere in between here, these bus voltages here, if this service disconnect is installed, then you could have 250 volts in, and that would electrocute you. And so we don't want to do that, so we have this service disconnect, and by pulling it, we lessen the chance that our technician who's messing around with the cable on B0 or the HVDC positive on B14, we don't want them to electrocute themselves, and so we basically have this service disconnect. Now, in the OEM pack, the BSU unit, it has a multiplexer here, and so it maintains this isolation. This needs to be galvanically isolated because any resistance you have across it is going to cause a galvanic isolation fault. And in your HVDC safety isolation stuff, you have to galvanically isolate this bus by pulling the service disconnect. Now you can see that when you install the signal soother, we violate that because now all of the circuit here in pink is basically bridging this isolation. This should be galvanically isolated, so when you run an impedance measurement or a DC high voltage leakage test or whatever, you should measure infinite resistance across this, and that's just not the case here. And all of these circuits in pink are violating that. So the B6, B5, B4, and B3 wires collectively, because of the way we're adding and then dividing, they violate that because we measure across that. So these op amps here and that op amp there are violating this service disconnect safety standard. And so what that means is that you could touch HVDC positive and HVDC negative with the service disconnect removed, and you could actually be dealt a lethal voltage. Now, every one of these signal soother elements has a 1K resistor. So at the end of the day, we have 5K at the top here, but it is in parallel with this one kind of as well. So it's probably closer to 3K to HVDC positive, and then your negative is maybe 1.5K, if you did the math to put those together. That's ultimately irrelevant because if you are going to have violations or whatever, they need to be in the 10 mega ohm range if you need to establish prevent a voltage breakdown from static charge. You could do two 5 mega ohm resistors in series, for example. So the point here ultimately is that if you remove the service disconnect here, the first claim that I made is that we are not actually splitting the pack in two because we have this alternate path through. The second claim is that when the service disconnect is removed, if you try to turn the car on, when this pre-charge resistor clicks over, again, we have maybe 15 ohms here. 250 volts divided by 15 ohms is, I don't really care about this service disconnect being there. This is essentially a short when it turns on initially because you're going into a capacitor. This is current limiting again, maybe to 16 amps, but that's irrelevant compared to the scale that we have here where we have these tiny little wires with 1K resistors and then 36 volt Zener diodes and op amps that are rated to 36 volts absolute max. So complicated circuit here, but this is ultimately the signal soother. Everything in blue is what the signal soother is faking basically on the battery input side. You can simplify this whole circuit down to the following test. So we have our HVDC positive bus and our HVDC negative bus again. I've brought the pre-charge resistor stuff over to here, and I've put again maybe 15 ohms. And here's our HVDC bus voltage. And here's the signal soother PCB. Probably should have highlighted that in blue, but the signals we care about are B3, B4, B5, and B6. We can take B7 through B14, which is all of these guys. And this is essentially a 144 volt, very low impedance power supply. For the purposes of the test I'm going to show, we're going to limit it to 2 amps because I don't want everything to blow up in my room. So yeah, that is going to be all of this stuff is going to be that power supply there. And then next we have our B6, which is on the high side of our V5 circuit. That's the silkscreen name on the signal soother PCB. And then, so we have 18 volts there. We're gonna have 18 volts across B5. We're gonna have our service disconnect. And then we have our B4. And then, so all of these, we basically have taps at B6 here, B5 here. Here's our service disconnect, B4, and then B3. So each one of these is a power supply that's simulating a blade, one of the Nextel modules. And then we have our negative, our HVDC negative voltage as well. And the point I'm going to make here is that when we put a load on this, we are going to generate the entire pack voltage because this load is going to be very, very low impedance, again, maybe 15 ohms versus, a few thousand ohms here. So all of that voltage drop is going to exist right here across the service disconnect. So let me show that to you here. I do have to put some PPE on, so it'll take a second. And once again, I'm not editing this video, so I got to put my earplugs on, my gloves, and some glasses. And I have over here, what we just hovered over was our 5 power supplies, and I'm going to turn those on. They are loud, so I do apologize for that. And I also have a programmable load, and let me just show you what's going on here. Move my chair. Okay, so this is just a vent hood. I'm not expecting it to catch all of the smoke here because I think there's going to be a lot of it. So I have all of these power supplies limited to either 1 or 2 amps. All of the blade voltages, so all the 18 volt supplies that I'm simulating are all limited to 2 amps. And the 144 volt, which is B7 through B14, and the B1 through B3 are both limited to 1 amp. So this is going to be quite a bit more current limited than in the car, where you essentially have an unlimited amount of current you can pull from these Nextel modules until they melt down. So what I'm going to do is I'm going to first, and then finally, this is the service disconnect here, which I'm going to disconnect while we're under test. This is to simulate the key on event here. Now the car is going to give up really quickly when it tries to turn on and the pack doesn't charge, or the HVDC bus doesn't charge. But that, even just that brief moment it's connected, it's essentially a 15 ohm short or whatever. That's going to be enough to totally fry this board. So what I'm going to do is I'm going to pop all of these supplies on here. And I haven't tested this, so bear with me. This is what science is. So I now have 252.7 volts applied across this guy here. And I'm going to put a 500 milliamp load across this. and turn that on. And so you can see we are pulling 500 milliamps. Let me show you very quickly. Well, anyway, we have a 500 milliamp load across this, and I'm going to now step away and remove this service disconnect. And we're gonna see what happens. I'm expecting bad things. So 1, 2, 3. I don't know if you saw those sparks on film. It blew out on V4 and V5. So now that we've finished that test, let me safely decommission this. Off, 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 and I'll pop all the power. I know these are loud power supplies. So you can saw we burned out. Honestly, that was quite a bit better than I thought it would be. But we did, of course, destroy that. I don't know if you saw them just incinerate in a ball of fire. I'm not sure which part is, but on the replay, which I'm probably playing right now, maybe, you can see that this did not fare well. There's no way this works anymore. I will, of course, test it. And if it is somehow working, I'll add an addendum, but I wouldn't expect to see that because there's no way this is going to work. So anyway, that's the test proving that there is a high voltage violation. We can pop back over to here. So what we just tested essentially, what we just tested, we blew out the here's where I saw sparks at least. Again, I was kind of safety squinting. V4 and V5. Definitely something happened somewhere. I don't know if it was the Zeners. You can probably even just tell. But we've totally ruined this. No, it was a fairly safe failure, but again, that guarantees that the first condition exists, that we're not getting this galvanic isolation. If this galvanic isolation did exist, which again, it does not, you just simply looking at the circuit shows you it does not, then when we disconnected the service disconnect, there would be no, this pink circuit basically wouldn't be in violation, and so you would essentially go to giga-ohms resistance and you wouldn't be able to push the 500 milliamps, it would collapse. So yeah, that, I mean, no surprises there. The only surprise maybe was that it didn't cause a bigger inferno. I was kind of expecting these guys, the dies on these to eject over to Mars or something, but probably just they open very quickly. We'll look at them under the scope, and if there's anything neat to look at, I'll show you, but that's exactly what I thought was going to happen, which is not surprising in any way, because science. So anyway, that confirms both the first and second theory, which I think have now been proven. If you have questions that are intelligent and would like to ask them, I would love to answer them. You know, if your question is, well, we stopped selling the signal soother, so I don't understand why you're testing it. The fact that this product exists at all and was offered as a mechanism to do whatever it is that it does, which we've discussed previously, which is basically lie to the computer about a failing pack. Questions like that I feel have already been thoroughly addressed, so I'm probably not going to spend too much time answering those further. But hey, look, 13-minute and 30-second video, that's pretty good for me. As always, thanks for watching.